Give importance, urgency, and inevitability to the advancement of space technology. The first of these factors is
the compelling urge of man to explore and discover, the thrust of curiosity that leads men to try to go where no one has gone before. Most of the surface of the Earth has been explored, and men now turn to the exploration of outer space as their next objective.
second,
There is the defense objective for the development of space technology. We wish to be sure that space is not used to endanger our security. If space is to be used for military purposes, we must be prepared to use space to defend ourselves.
There is the factor of national prestige. To be strong and bold in space technology will enhance the prestige of the United States among the peoples of the world and create added confidence in our scientific, technological, industrial, and military strength.
and fourth.
Space technology affords new opportunities for scientific observation and experiment, which will add to our knowledge and understanding of the Earth, the solar system, and the universe.
The determination of what our space program should be must take into consideration all four of these objectives. While this statement deals mainly with the use of space for scientific inquiry, we fully recognize the importance of the other three objectives. In fact, it has been the military quest for ultra-long-range rockets that has provided man with a new machinery so powerful that it can readily put satellites in orbit and, before long, send instruments out to explore the moon and nearby planets. In this way, what was at first a purely military enterprise has opened up an exciting era of exploration that few men, even a decade ago, dreamed would come in this century.
Why do satellites stay up?
The basic laws governing satellites and space flight are fascinating in their own right, and while they have been well known to scientists ever since Newton, they may still seem a little puzzling and unreal to many of us. Our children, however, will understand them quite well.
I know that the harder I throw a stone, the farther it will travel before falling to earth. I could imagine my strength so fantastically multiplied that I could throw a stone at a speed of 15,000 miles per hour, and it would travel a great distance. It would, in fact, easily cross the Atlantic Ocean before the Earth's gravity pulled it down. Now, imagine being able to throw the stone just a little faster, say about 18,000 miles per hour. What would happen then?
The stone would again cross the ocean, but this time it would travel much farther than it did before. It would travel so far that it would overshoot the Earth, so to speak, and keep falling until it was back where it started. Since, in this imaginary example, there is no atmospheric resistance to slow the stone down, it would still be traveling at its original speed, 18,000 miles per hour, when it got back to its starting point. So, around the Earth it goes again. From the stone's point of view, it's continually falling, except that its very slight downward arc exactly matches the curvature of the Earth, and so it stays aloft, or, as the scientist would say, in orbit, indefinitely.
Since the Earth has an atmosphere, of course, neither stones nor satellites can be sent whizzing around the Earth at treetop level. Satellites must first be lifted beyond the reach of atmospheric resistance. It is absence of atmospheric resistance plus speed that makes the satellite possible. It may seem odd that weight or mass has nothing to do with the satellite's orbit. If a feather were released from a 10-ton satellite, the two would stay together following the same path in the airless void. There is, however, a slight vestige of atmosphere even a few hundred miles above the Earth, and its resistance will cause the feather to spiral inward toward the Earth sooner than the satellite. It is atmospheric resistance, however slight, that has set limits on the life of all satellites launched to date. Beyond a few hundred miles, the remaining trace of atmosphere fades away so rapidly that tomorrow's satellite should stay aloft thousands of years and perhaps indefinitely. The higher the satellite, incidentally, the less speed it needs to stay in orbit once it gets there. Thus, the moon's speed is only a little more than 2,000 miles per hour. But to launch a satellite toward a more distant orbit requires a higher initial speed and greater expenditure of energy.
Rocket engineers rate rockets not in horsepower, but in thrust. Thrust is just another name for push, and it is expressed in pounds of force. The rocket gets its thrust or push by exhausting material backward. It is this thrust that lifts the rocket off the Earth and accelerates it, making it move faster and faster.
As everyone knows, it is more difficult to accelerate an automobile than a baby carriage. To place satellites weighing 1,000 to 2,000 pounds in orbit requires a first-stage rocket engine, or engines, having a thrust in the neighborhood of 200,000 to 400,000 pounds. Rocket engines able to supply this thrust have been under development for some time. For launching a satellite or other space vehicle, the rocket engineer divides his rockets into 2, 3, or more stages, which can be dropped one after the other in flight, thus reducing the total weight that must be accelerated to the final velocity desired. In other words, it is a great waste of energy to lift one huge fuel tank into orbit when the tank can be divided into smaller tanks, each packaged in its own stage with its own rocket motor that can be left behind as they become empty.
To launch some of the present satellites has required rockets weighing up to 1,000 times the weight of the satellite itself. But it will be possible to reduce takeoff weights until they are only 50 to 100 times that of the satellite. The rocket's high ratio of gross weight to payload follows a fundamental limitation in the exhaust velocities that can be achieved by chemical propellants.
If we want to send up not a satellite, but a device that will reach the moon, we need a larger rocket relative to its payload in order that the final stage can be accelerated to about 25,000 miles per hour. This speed, called the escape velocity, is the speed with which a projectile must be thrown to escape altogether from the gravitational pull of the Earth. If a rocket fired at the moon is to use as little fuel as possible, it must attain the escape velocity very near the beginning of its trip. After this peak speed is reached, the rocket will be gradually slowed down by the Earth's pull, but it will still move fast enough to reach the moon in 2 or 3 days.
Moon exploration will involve 3 distinct levels of difficulty. The first would be a simple shot at the moon, ending either in a hard landing or a circling of the moon. Next in difficulty would be a soft landing, and most difficult of all would be a soft landing followed by a safe return to Earth.
The payload for a simple moonshot might be a small instrument carrier similar to a satellite. For the more difficult soft landing, the carrier would have to include, as part of its payload, a retro rocket, a decelerating rocket, to provide braking action, since the moon has no atmosphere that could serve as a cushion.
To carry out the most difficult feat, a round trip to the moon, will require that the initial payload include not only retro rockets, but rockets to take off again from the moon. Equipment will also be required aboard to get the payload through the atmosphere and safely back to Earth. To land a man on the moon and get him home safely again will require a very big rocket engine indeed, one with a thrust in the neighborhood of 1 or 2 million pounds. While nuclear power may prove superior to chemical fuels in engines of the multi-million-pound thrust, even the atom will provide no shortcut to space exploration.
Sending a small instrument carrier to Mars, although not requiring much more initial propulsion than a simple moonshot, would take a much longer travel time, 8 months or longer, and the problems of navigation and final guidance are formidable.
Fortunately, the exploration of the moon and nearby planets need not be held up for lack of rocket engines big enough to send men and instrument carriers out into space and home again. Much that scientists wish to learn from satellites and space voyages into the solar system can be gathered by instruments and transmitted back to Earth. This transmission, it turns out, is relatively easy with today's rugged and tiny electronic equipment.
For example, a transmitter with the power of just 1 or 2 watts can easily radio information from the moon to the Earth. and messages from Mars, on the average some 50 million to 100 million miles away at the time the rocket would arrive, can be transmitted to Earth with less power than that used by most commercial broadcasting stations. In some ways, indeed, it appears that it will be easier to send a clear radio message between Mars and Earth than between New York and Tokyo.
This all leads up to an important point about space exploration. The cost of transporting men and material through space will be extremely high, but the cost and difficulty of sending information through space will be comparatively low.
Will the results justify the costs?
Since the rocket power plants for space exploration are already in existence or being developed for military need, the cost of additional scientific research using these rockets need not be exorbitant. Still, the cost will not be small either. This raises an important question that scientists and the general public, which will pay the bill, both must face. Since there are still so many unanswered scientific questions and problems all around us on Earth, why should we start asking new questions and seeking out new problems in space? How can the results possibly justify the cost?
Scientific research, of course, has never been amenable to rigorous cost accounting in advance, nor, for that matter, has exploration of any sort. But if we have learned one lesson, it is that research and exploration have a remarkable way of paying off, quite apart from the fact that they demonstrate that man is alive and insatiably curious. And we all feel richer for knowing what explorers and scientists have learned about the universe in which we live.
It is in these terms, then, that we must measure the value of launching satellites and sending rockets to space. These ventures may have practical utility, some of which will be noted later. But the scientific questions come first.
Here are some of the things that scientists say can be done with the new satellites and other space mechanisms. A satellite in orbit can do three things. One,
it can sample the strange new environment through which it moves.
Two,
it can look down and see the Earth as it has never been seen before.
And three,
it can look out into the universe and record information that can never reach the Earth's surface because of the intervening atmosphere.
The satellite's immediate environment at the edge of space is empty only by earthly standards. Actually, empty space is rich in energy, radiation, and fast-moving particles of great variety. Here we will be exploring the active medium, a kind of electrified plasma dominated by the sun, through which our Earth moves. Scientists have indirect evidence that there are vast systems of magnetic fields and electrical currents that are connected somehow with the outward flow of charged materials from the sun. These fields and currents the satellites will be able to measure for the first time. Also, for the first time, the satellites will give us a detailed three-dimensional picture of the Earth's gravity and its magnetic field.
Physicists are anxious to run one crucial and fairly simple gravity experiment as soon as possible. This experiment will test an important prediction made by Einstein's general theory of relativity, namely, that a clock will run faster as the gravitational field around it is reduced. If one of the fantastically accurate clocks using atomic frequencies were placed in a satellite and should run faster than its counterpart on Earth, another of Einstein's great and daring predictions would be confirmed.
This is not the same as the prediction that any moving clock will appear to a stationary observer to lose time, a prediction that physicists already regard as well confirmed.
There are also some special questions about cosmic rays which can be settled only by detecting the rays before they shatter themselves against the Earth's atmosphere. And of course, animals carried in satellites will begin to answer the question, what is the effect of weightlessness on physiological and psychological functions?
You see, gravity is not felt inside a satellite because the Earth's pull is precisely balanced by centrifugal force. This is just another way of saying that bodies inside a satellite behave exactly as they would inside a freely falling elevator.
the satellite that will turn its attention downward holds great promise for meteorology and the eventual improvement of weather forecasting. Present weather stations on land and sea can keep only about 10% of the atmosphere under surveillance. 2 or 3 weather satellites could make a cloud inventory of the whole globe every few hours. From this inventory, meteorologists believe they could spot large storms, including hurricanes, in their early stages and chart their direction of movement with much more accuracy than at present.
Other instruments in the satellite will measure for the first time how much solar energy is falling upon the Earth's atmosphere and how much is reflected and radiated back into space by clouds, oceans, the continents, and by the great polar ice fields.
It is not generally appreciated that the Earth has to send back into space over the long run exactly as much heat energy as it receives from the sun. If this were not so, the Earth would either heat up or cool off. But there is an excess of income over outgo in the tropical regions and an excess of outgo over income in the polar regions. This imbalance has to be continuously rectified by the activity of the Earth's atmosphere, which we call weather.
By looking at the atmosphere from the outside, satellites will provide the first real accounting of the energy imbalances and their consequent tensions all around the globe. With the insight gained from such studies, meteorologists hope they may improve long-range forecasting of world weather trends.
Finally, there are the satellites that will look not just around or down, but out into space. Carrying ordinary telescopes as well as special instruments for recording X-rays, ultraviolet, and other radiations, these satellites cannot fail to reveal new sights forever hidden from observers who are bound to the Earth. What these sights will be, no one can tell. But scientists know that a large part of all stellar radiation lies in the ultraviolet region of the spectrum, and this is totally blocked by the Earth's atmosphere. Also blocked are other very long wavelengths of light, of the kind usually referred to as radio waves. Some of these get through the so-called radio window in the atmosphere and can be detected by radio telescopes. But scientists would like a look at the still longer waves that cannot penetrate the Earth.
Even those light signals that now reach the Earth can be recorded with brilliant new clarity by satellite telescopes. All existing photographs of the Moon and nearby planets are smeared by the same turbulence of the atmosphere that makes the stars twinkle. Up above the atmosphere, the twinkling will stop, and we should be able to see for the first time what Mars really looks like. And we shall want a really sharp view before launching the first rocket to Mars.
While these satellite observations are in progress, other rockets with other kinds of instruments will be striking out for the Moon.
Photographs of the back or hidden side of the Moon may prove quite unexciting, or they may reveal some spectacular new feature now unguessed. Of greater scientific interest is the question whether or not the Moon has a magnetic field. Since no one knows for sure why the Earth has such a field, the presence or absence of one on the Moon should throw some light on the mystery.
But what scientists would most like to learn from a close-up study of the Moon is something of its origin and history. Was it originally molten? Does it now have a fluid core similar to the Earth's? And just what is the nature of the lunar surface? The answer to these and many other questions should shed light, directly or indirectly, on the origin and history of the Earth and the surrounding solar system.
While the Moon is believed to be devoid of life, even the simplest and most primitive, this cannot be taken for granted. Some scientists have suggested that small particles with the properties of life, germs or spores, could exist in space and could have drifted onto the Moon. If we are to test this intriguing hypothesis, we must be careful not to contaminate the Moon's surface in the biological sense beforehand. There are strong scientific reasons, too, for avoiding radioactive contamination of the Moon until its naturally acquired radioactivity can be measured.
The nearest planets to Earth are Mars and Venus. We know quite enough about Mars to suspect that it may support some form of life.
To land instrument carriers on Mars and Venus will be easier in one respect than achieving a soft landing on the Moon. The reason is that both planets have atmospheres that can be used to cushion the final approach. These atmospheres might also be used to support balloons equipped to carry out both meteorological soundings and a general photo survey of surface features. The atmosphere of Venus, of course, consists of what appears to be a dense layer of clouds so that its surface has never been seen at all from Earth. Remotely controlled scientific expeditions to the moon and nearby planets could absorb the energies of scientists for many decades. Since man is such an adventurous creature, there will undoubtedly come a time when he can no longer resist going out and seeing for himself. It would be foolish to try to predict today just when this moment will arrive. It might not arrive in this century, or it might come within 1 or 2 decades. So much will depend on how rapidly we want to expand and accelerate our program. According to one estimate, it might require a total investment of about a couple of $2 billion spent over a number of years to equip ourselves to land a man on the moon and to return him safely to Earth.
Meanwhile, back at the Earth, satellites will be entering into the everyday affairs of men. Not only will they be aiding the meteorologists, but they could surely and rather quickly be pressed into service for expanding worldwide communications, including intercontinental television. At present, all transoceanic communication is by cable, which is costly to install, or by shortwave radio, which is easily disrupted by solar storms. Television cannot practically be beamed more than a few hundred miles because the wavelengths needed to carry it will not bend around the Earth and will not bounce off the region of the atmosphere known as the ionosphere. To solve this knotty problem, satellites may be the thing, for they can serve as high-flying radio relay stations. Several suitably equipped and properly spaced satellites would be able to receive TV signals from any point on the globe and to relay them directly and perhaps via a second satellite to any other point. Powered with solar batteries, these relay stations in space should be able to keep working for many years.
The development of military rockets has provided the technological base for space exploration. It will probably continue to do so because of the commanding military importance of the ballistic missile. The subject of ballistic missiles lies outside our present discussion. We ask instead, putting missiles aside, what other military applications of space technology can we see ahead?
There are important foreseeable military uses for space vehicles. These lie, broadly speaking, in the fields of communication and reconnaissance. To this, we could add meteorology, for the possible advances in meteorological science, which have already been described, would have military implications. The use of satellites for radio relay has also been described, and it does not take much imagination to foresee uses of such techniques in long-range military operations.
The reconnaissance capabilities of a satellite are due, of course, to its position high above the Earth and the fact that its orbit carries it in a predictable way over much of the globe. Its disadvantage is its necessarily great distance, 200 miles or more from the surface. A highly magnifying camera or telescope is needed to picture the Earth's surface in even moderate detail. To the human eye, from 200 miles away, a football stadium would be a barely distinguishable speck. A telescopic camera can do a good deal better depending on its size and complexity. It is certainly feasible to obtain reconnaissance information with a fairly elaborate instrument, information which could be relayed back to the Earth by radio.
Much has been written about space as a future theater of war, raising such suggestions as satellite bombers, military bases on the moon, and so on. For the most part, even the most sober proposals do not hold up well on close examination or appear to be achievable at an early date. Granted that they will become technologically possible, most of these schemes nevertheless appear to be clumsy and ineffective ways of doing a job. Take one example, the satellite as a bomb carrier. A satellite cannot simply drop a bomb. An object released from a satellite doesn't fall, so there is no special advantage in being over the target. Indeed, the only way to drop a bomb directly down from a satellite is to carry out aboard the satellite a rocket launching of the magnitude required for an intercontinental missile. A better scheme is to give the weapon to be launched from the satellite a small push, after which it will spiral in gradually. But that means launching it from a moving platform halfway around the world with every disadvantage compared to a missile on the ground. In short, the Earth would appear to be, after all, the best weapons carrier.
This is only one example. Each idea has to be judged on its own merits. There may well be important military applications for space vehicles which we cannot now foresee, and developments in space technology which open up quite novel possibilities. The history of science and technology reminds us sharply of the limitations of our vision. Our road to future strength is the achievement of scientific insight and technical skill by vigorous participation in these new explorations. In this setting, our appropriate military strength will grow naturally and surely.
Thus, we see that satellites and space vehicles can carry out a great variety of scientific missions and a number of military ones as well. Indeed, the scientific opportunities appear so numerous and so inviting that scientists from many countries will certainly want to participate. Perhaps the International Geophysical Year will suggest a model for the international exploration of space in the years and decades to come.
Have we a space timetable?
We do. The following timetable suggests the approximate order in which some of the scientific and technical objectives mentioned in this review may be attained. The timetable is not broken down into years, since there is yet too much uncertainty about the scale of the effort that will be made. The timetable simply lists various types of space investigations and goals under 3 broad headings.
Early, later,
Still later.
What are some of the scientific objectives to be served early?
Physics, geophysics, meteorology.
minimal moon contact, experimental communications, space physiology.
And later?
Astronomy, extensive communications, biology, scientific lunar investigation, minimal planetary contact, human flight in orbit.
And still later?
Automated lunar exploration,
Automated planetary exploration.
Human lunar exploration and return.
Human planetary exploration.
In conclusion, then, we might venture 2 observations.
research in outer space affords new opportunities in science, but it does not diminish the importance of science on Earth. Many of the secrets of the universe will be fathomed in laboratories on Earth, and the progress of our science and technology and the welfare of the nation require that our regular scientific programs go forward without a loss of pace. In fact, at an increased pace. It would not be in the national interest to exploit space science at the cost of weakening our efforts in other scientific endeavors.
This need not happen if we plan our national program for space science and technology as part of a balanced national effort in all science and technology.
Our second observation is prompted by technological considerations. For the present, the rocketry and other equipment used in space technology must usually be employed at the very limit of its capacity. This means that failures of equipment and uncertainties of schedule are to be expected.